That said, our first speaker is Darryl Havens. His title is Senior Software Design Engineer, but he's actually the I/O System Architect. Darryl has been with the NT team since the very beginning. In fact, a good reason that NT exists as it does today is probably Darryl. That's true. Darryl is freshly back from a extended vacation, and I'll let him tell you all about it if he wants to. And that said, here's Darryl.
Well, I don't know how responsible I am for NT being here, but the team that actually did NT has been together for a long, long time. Some of us worked for another corporation before we came to Microsoft. We started this project in '88, but some of us have actually worked together since 1977, so we have a lot of experience working on various products and stuff like that. Before I begin, I'd like to say that I'd like to welcome everyone here, first of all. Second of all, I don't mind questions. I would like to do them at the end, however, otherwise it will interrupt my flow. And this should be a real interesting and entertaining talk since, according to my time, which is, I just came over from Spain, I should be just finishing up the siesta that I just missed. So if I fall asleep during this, if someone could just come up and nudge me, get me back awake, that'd be great. How many people in here, let me just see this room since I can't see the other room. How many people are here because they're interested in writing a file system for an honest structure? Okay, so a dozen or so. And how many people are interested in network file systems, i.e. servers or redirectors? Holy, are you guys in for a surprise? And how many people are interested in hierarchical storage management? So about the same as ODS. And how many people are interested in filter drivers? And what I mean, okay, wow. Okay, interesting. Yeah, for those of you who are used to running TSRs and stuff like that, as you probably already know, we don't have any of those kinds of things. So a filter driver is the way you capture all the opens to all the files in the system. And filter drivers are interesting little animals. One last question. How many people have already attended the DDK seminars and conferences that we've done in the past, or already written a device driver for NT? Oh, good. Okay. That's great. How many people don't know anything about the internals of NT? Well, that's really good. Okay. Okay, great. Well, let's start off then. And is the left button? Yeah, great. Okay. Very briefly, I'd like to cover some of the goals that we had when we started this project in the first place. Obviously, the biggest goal was to get rid of that, I won't say that, just how about let's call it DOS. The first goal was to make the operating system portable, and what I mean by portable in this particular case is we wanted to make the operating system portable across different hardware architectures. Today, Windows NT runs on the Intel x86 architecture. It runs on MIPS machines, our 4000s, 4400As. Those are really blazingly fast machines. Also runs on Digital's Alpha. In order to make the thing portable, we had to make some design decisions up front about what language we were going to write the thing in, et cetera, et cetera. As you probably know, we chose C. Another goal that we had was to make the operating system secure. That is to say that we want to get a C2 certification from the government, and we're currently in the midst of doing that. Actually, we're in the final stages of doing that. And Jim Kelly, when he comes up and talks to you, I think tomorrow, will tell you a little bit about that process and what we've had to do to make it secure. And it truly is secure, i.e. C2 certification. We have a migration path to B. Don't know whether we'll actually do that. So everybody know the difference between a C and a B? One is discretionary access control, that's C. And B is mandatory access control, where you have different security levels and then different departments. For example, you're in the Navy and you have top secret clearance, or you're in the Army and you only have secret or whatever. That's mandatory access control. And Jim will hopefully explain some of that to you. A third goal that we had was compatibility. Compatibility with, we need to be able to run DOS applications. We don't run all DOS applications for the same reason that we have a security certification, i.e. we don't let applications go and diddle hardware directly. There are some ways that we allow people to get to things like frame buffers for the video and stuff like that, but you cannot today, nor will you ever be able to, I hope, be able to sit in application and program the DMA. That's just not something that we can allow people to do, because as soon as you start programming the DMA controller, now you can say, well, I'd like to take this physical address over here, which happens to be in that guy's virtual address space, and DMA it out to my device, or DMA it into my buffer, and look at things that you're not supposed to be able to look at. We also have to be able to run Windows applications and stuff like that, and OS2 applications, et cetera, et cetera. We want the operating system to be extensible, and part of that is why you're all here today. That is to say, if the operating system is to be a worldwide, world-class, true operating system, then you need to be able to extend it and take care of other on-disk structures and stuff like that. For example, BSD or Andrew or what have you. We wanted the operating system to be robust. That is to say, if an application decides to crash, it just crashes the application, not the whole system. Gosh, what a concept. I was talking to a person on the plane, as a matter of fact, on my way to Europe a couple of weeks ago. And this person had heard about Windows NT and wanted to know why he wanted to use it. And I said, what do you do? And he says, well, I'm a writer, and I just write. I said, well, then you probably don't need to use it at all. And after we talked for a little while, he started asking me some of the features, and I started talking about logging file systems and stuff like that. And he said, well, wait a minute, what's that mean? So I explained what a logging file system does, and he said, well, does that mean that if the system crashes, I don't lose all my data if it's been flushed to the disk? And I said, yeah. He says, I'm buying Windows NT. I said, well, never mind, I won't tell you what application it was running. It was a competitor's word processing. Yes, right. Word wouldn't crash, though, right? Yeah, right. Okay, another goal is symmetric multiprocessing. Today, there aren't any operating systems in the low end out there that support multiprocessing, i.e. multiple processors in the system running simultaneously at the same time. I don't know why that got to be a joke, but that got to be a joke in our group. Another one is connectivity. We'd like to be able to support everybody, i.e. all you guys in here that raised your hand when I said network file systems. That's great. That's awesome. I mean, we want to support not just Novell and Microsoft and SNA, but we'd like to support everything else, Banyan, Vines, et cetera, et cetera. And you can help us do that. And then finally, we wanted to make the product very easy to internationalize, and it seems that we've been able to do that. We're already selling this stuff in a big way in Europe and in other places in the world. Okay, let's briefly take a look at the system structure for Windows NT. If one draws a block diagram of what the Windows NT system structure looks like, what you have is this picture that I've shown up here. Wow, lots of mouse cord. Can I get more mouse cord? Dave? Nope, guess not. Okay, let's see if I can use this thing to draw. Oh, this is going to be real. Oh, that didn't work. Can I get some more cord out of this thing?
I'm coming.
Okay. I'd like to draw with.
Do you know how to draw?
Version 4? Oh, no. Oh, it's version 4? Great. Oh, well. If you take a look at where the Windows NT executive line is in the center of the structure, and if you draw a line between that and where it says LPC, everything above that line runs in user mode. Everything below that runs in kernel mode, i.e. everything above is is either an application or an operating system emulation subsystem or some kind of service or daemon. Those are all user mode applications and processes. And the reason that they're out there is so that those kinds of things can't crash the system. For example, even if the OS2 subsystem running an OS2 application has a bug in it and crashes, it won't take down the rest of the system. Therefore, because the executive is still running, we can still go ahead and save your files and not take down the file system. Everything below it runs in kernel mode. It's all in privileged mode, and that's where we're going to be spending all of the time that we have here in the next couple of days. Okay, so how do subsystems work? A subsystem, an operating system emulation subsystem, works using a client service model. That is, what we do is the application makes a call to the subsystem, and the subsystem then performs the operation on behalf of the application. For example, if the application says that what it would like to do is it would like to open a file, then it doesn't call NT directly. It calls like DOS open, for example. DOS open then decides whether or not what it needs to do is call directly down into the executive or go over to another process, which is the operating system emulation subsystem that we saw on this previous screen. Up here, for example, that would be the little box in pink, which is the Win32 system. That is the process that represents that emulation subsystem. Now, it's not necessary that all of those calls go to the subsystem. For example, in Win32, there are no I/O calls that actually involve the subsystem process. Okay, they all go directly through a DLL on the client side down into the Windows NT executive, or they go down into the DLL, come right back, and the DLL says, "Oh, I already did that." For some emulation subsystems, however, for example, file locks in POSIX are advisory, not mandatory. Therefore, there's no way to do file locks inside all the DLLs, and file locks that are inside Windows NT are mandatory, not advisory, so you actually have to involve subsystem whenever you would like to do a file lock in POSIX. Obviously, the best way to run a subsystem, if you can possibly do it, is to not make the transition to that other process, because that involves context switch. But in some cases, you have to go do that, and that state is in that subsystem. And we optimize a lot of different things, and we'll talk about some of those as we go along if we have the time. The ability to write a subsystem in user mode gives you the ability to absolutely control everything that's going on inside the client application. That is to say that if a client application comes along and says it wants to create a process, you, the operating system emulation subsystem, have control over what that process can do to the process that it just created. For example, you can say that that process doesn't actually have the privilege to go kill the process that it just created. In other words, it would have to come through you in order to do that. So by not giving it the access, you can control what it's doing. And there are no semantics imposed on the subsystem by the underlying operating system. Think of the operating system itself as a set of building blocks that you can use to go emulate some other operating system. This is very much like CMU's mock operating system. If a process creates a subprocess or a child process, Windows NT itself imposes no restrictions or any protocols on what the interrelationship between those two processes is. That's up to the operating system emulation subsystem. So, for example, one operating system emulation subsystem may say that the relationship between the two processes is the second process is a child, and if the first process goes away, then the child process goes away as well. But it's up to the subsystem to make that happen, not Windows NT. Because in other operating systems, that's not the relationship. Okay, does everyone understand that? Okay, great. Okay, Win32 is the operating system emulation interface that we have on Windows NT to support what we would call the native if you will, subsystem. And Win32 is obviously supported on not only Windows NT, but on future versions of, well, everyone knows Chicago, so we'll just call it Chicago. So what you can see here is that there are actually different emulation subsystems based on what kind of operating system interface you're talking about. So we have MS-DOS over on the left, and that application talks directly to the MS-DOS BDM emulation subsystem. Win16 goes through a thunk to get you to Win32. Win32 applications talk directly to the Win32 subsystem, and in these cases, subsystem down here is referring to both the client DLL and to the subsystem process that's created if you actually need one. In these cases, you actually do. OS2 apps talk to the OS2 subsystem, and POSIX applications talk to the POSIX subsystem. And then each one of those, like I said before, either implements the API that the person called, that the application called, or else they go down to the kernel to get it done on behalf of them. Examples of some of the Windows NT subsystems we have today are Security Authority, and Jim will talk some about that tomorrow. It actually is a subsystem, and it talks to the executive. There's a piece of the security system inside the executive as well. It's a privileged kernel mode piece. The Windows subsystem is another subsystem which includes MS-DOS and the Windows 3.x wrapper. POSIX subsystem, OS2 subsystem, the debug system, and as we saw before, the Win32 subsystem. Okay, here's an explanation, a slide that actually explains the different pieces of the contents of a subsystem, which is the client-side DLL, which implements the emulated API either. It just implements the API. It has the state inside the DLL to say, I'm done, and simply returns. Okay, so all we've done is we've made a call to another user mode piece from the application, returns back and says, okay, I'm done. Or it may have to call the subsystem, i.e. the other process, and it does that by marshalling up the arguments and then calling via LPC the other subsystem, passing those arguments over. The subsystem then performs the operation and returns back. And then the third way to do it is to call the NT executive itself. The subsystem is responsible for starting and stopping clients, and it's also responsible for maintaining global state for everything within that. Okay, that's it for user mode. I don't think we're going to talk about user mode the whole rest of this conference. The rest of it will all be in Windows NT Executive, and primarily we'll spend most of our time in the I/O system. This morning what I'll do for the rest of this talk is talk about all the components of the executive and how they fit together, and then the second talk after the break we will talk exclusively about the I/O system and then dive down from there into each of the individual components over the next couple of days. Okay, so what is the Windows NT Executive? The Windows NT Executive is layered on top of the kernel. If you go back to the previous page, the kernel is this little bit over here on about the middle right. So we're going to distinguish between the kernel and the executive. The kernel is a really small piece of the executive, and I'll explain what that thing actually does in a few minutes. But the executive, think of the executive as everything that runs in kernel mode, and in order to get into the executive, you have to go through that line, the transition from user mode to kernel mode. Okay, so we're actually making a state transition from a non-privileged mode into a privileged mode. It is, the Windows NT Executive is the interface to user mode, and that's how we get there. There are a set of what we call system services, or NT APIs, that you can use to make the transition from user mode into kernel mode. And the executive itself consists of a bunch of little components, each of which has a very formal, well-defined interface. So if you wanted to, for example, you could rip out the I/O system inside of the executive, and as long as you implemented the same I/O APIs, then you could replace that entire piece. You could do the same thing for the kernel or the object manager, et cetera, et cetera. And we suspect that eventually people will want to do things like that. One of the things that universities are apparently very interested in is taking Windows NT, taking the specification for, say, example, the memory manager, and then allowing students to replace the entire memory manager with an entire new memory manager that simply implements those APIs. So in other words, instead of writing a compiler, you would say, here's a set of APIs, you have to implement those on this particular architecture, and that would be a class project or something like that for some university students. Okay, the executive components then we're going to be talking about, these are the primary components, are the object manager, the memory manager, the I/O subsystem, which we're going to spend a lot of time on, the process communication, process structure, and the security subsystem. And what is the object manager? Well, we've said that in the past that Windows NT is an object-based system. I prefer to use the word pseudo-object because the word object has just gotten so overused these days. Everything's object-oriented. Well, what's that mean? To me, when I say that Windows NT is a pseudo-object-oriented operating system, what I mean by that is if you are a user mode subsystem and you're using the Windows NT executive to implement a set of interfaces, then the interface that you really have to the operating system or to the executive is you create an object, you create an entity for which you get back an opaque handle which you can perform operations on. In a truly object-oriented system, you can call those things methods. So now you have a handle. When you created the object, you told the operating system what kind of access you'd like to have to that particular object. You can name the object. By naming it, you can also share it. You can give the name to someone else in another process. That process can then open the same object, giving it a set of desired access that it would like to have, and by being able to put an access control list, an ACL, on the object, you can control what various people can do to that particular object. But what you get back is a handle. It's an opaque handle. You can't do anything with that handle except for call other APIs and say, I'd like to do this or that or the other. The security that's involved in the object system is it decides, the object system and security manager decide together based on who you are, based on a token for your particular process, and the ACL on the particular object that you're trying to open or create. They then decide together what you're actually allowed to do to that object. Okay? Once you've decided that, you get back this handle, and now when you go to perform an operation, it's a simple bit test to determine whether or not you're allowed to perform that particular operation on that particular object given that particular handle. Okay, so for example, if I wanted to open a file, I could open a file and say that I would like to have read-write access. What happens is the object manager calls the file system says, oh, he would like read-write access, takes your token, takes the ACL on the file and calls the security manager and said, this person would like to have read-write access to this particular object. Are they allowed to do that? The security system looks through the ACL, figures out who you are, and determines whether or not you're allowed to do that. If you are allowed to do that, then you get back a handle that has read-write access to that particular object. Okay? When you then come in later and say, I would like to do a read, the I/O system takes your handle, calls the object manager and says, this person is trying to open, or is trying to perform a read operation on this particular object using this handle. Is he allowed to do that? Well, the object manager simply takes the read bit, takes the access mask that we stored for what you're allowed to do, does a test and says, is this person allowed to do that? If it comes out yes, the answer is yes. It's a simple bit test, okay? So from then on, the security is really cheap. All the security happens way up front. Okay, object handles to each one of these objects are per process specific. That is to say, once I've created a handle to an object, I can't then pass that to another process and expect that process to be able to do something to it. Okay? I can, well, we won't get into what you can do. Basically, that's how it works. Once you've got a handle, that handle is specific to your process. Access validation is via these access control lists, ACLs. Those is simply a list of all the people that can do all the particular accesses to that particular object. And the object manager is the person who, or the component of, it's Steve Wood, no, is the component that exports the functions to build all of these user visible objects such as processes and threads and events and files and et cetera, et cetera. The memory manager is the component of the executive that provides the space, the virtual address space, in which applications execute. It's a 32-bit address space, therefore it's 4 gig. It's broken into a user address space and a system address space. The lower 2 gig are for user, and the upper 2 gig are for the system. It's a demand paged memory environment. What that simply means is you get pages based on what pages you touch. So once you've touched the page, we go and get it and we bring it into what's called your working set, which Lou will explain to you tomorrow. Once the page is in your working set, you can access it until it either gets kicked out of your working set or until you blow away your virtual address space. The memory manager exports memory mapped files, and for those of you who are going to be writing file systems, there are of the first 3 type, i.e. network, ODS, and HSM, you'll need to worry about map files because they are the way in which, for example, when you go to execute an image, what we do is we take the image and we map it in your virtual address space. We do that via these map files, and the memory manager along with the file system and the cache manager all work together to map a view of that particular file into the address space. So that's some pretty interesting stuff and causes some interesting situations inside of the executive and file systems. We do allow cross-process operations. One of the ways that subsystems can control the processes that are part of their subsystem is we'll allow processes to actually read and write virtual address space in another process. Obviously, these are very highly privileged operations, but we do allow you to be able to do things like that. We also support what are called copy on write pages and guard page. A copy on write page says, I'm going to take a bunch of pages and I'm going to make them, let's say, read only. If I touch one of those pages in a write, using a write operation, what I'd like you to do is I'd like you to take and make another physical copy of that page, and now that's my private copy of the page that I was sharing with everyone else before. A guard page is a page which causes a particular type of violation to the operating system that it understands, and we use these to allow us to have growable, expandable user stacks. So what you would do is you'd say, well, let's say the user has 2 pages of user stack. At the bottom of the stack, or the top of it, depending on how you look at the way stacks look, you place a guard page, and as the user's application runs, it will begin to touch those pages and will take what's called a guard page violation, and that simply says, oh, this is a page that doesn't exist yet, go get a real page and back it up, and if we're running out of virtual address space, then we can actually bubble those things up and get them handled in other ways. For example, we can tell the application, you're actually running out of stack space and you don't have any more. You need to do something about this because you're using too much stack. The memory manager also supports multiple paging files. You have multiple paging files on multiple spindles in the system. So you don't have to have them all on in one. You don't have to have one paging file. It doesn't have to necessarily be on the disk that you booted from, et cetera, et cetera. And the memory manager also works with the cache manager to provide this single global cache manager cache. Some of the features of the I/O system component are we support an asynchronous I/O model that has a 64-bit file address. That is to say that files can be 64 bits long. Applications can read and write to the whole address space inside the file using a 64-bit file offset. It exports file objects. File objects have an open, a close, and an operate semantic. Operations being such things as read, write, et cetera, and we'll talk a whole lot about what those services are. We also provide, the I/O system also provides services for drivers and file systems through the same formal model that all the other components provide to each other and to file systems. Drivers and file systems in this operating system are written in C, period. There is no support for writing your file system or your driver in assembler, for example. There are no ASM header files. You need to write all these things in C. If you write them in C and you follow all the rules and all the guidelines that we provide you, then your file system and your device driver will not only run in a portable way on an x86, but it's very easy to migrate to other platforms. And we'd like you to be able to do that. We'd like to be able to say, you know, well, okay, everything runs except for this one file system won't run on MIPS because the guys who designed it didn't do a very good job of following the rules. The other thing that you need to watch out for when you're writing these things is what happens when the user decides, geez, I'd like a multi-processor Pentium. So what I'm going to do is I'm just going to plug in a processor, and bingo, your file system is supposed to work. Well, will it? Good question. If you follow the rules and guidelines that we have, then it's very simple to get that right. CLI, as the CLI instruction, doesn't do much when there's another processor involved, right? You can turn off the interrupts on your particular processor, but that doesn't do any good if this truly is a symmetric multiprocessing system, and now the device can interrupt on another processor, and your file system can get called on that other processor when you thought that you weren't allowed to get called. The I/O system works with the memory manager and the cache manager to provide a single integrated cache subsystem. Part of, or one of the features of the I/O subsystem is the NTFS file system. This is NT's native file system. It supports very large disks and files. It actually uses 64-bit file offsets for everything that it does. It has crash recovery. For those of you who've used the file systems that we've supported in the past that weren't fat, and had your system crash on a multi-gigabyte disk, and then watch check disk run for, what, days, you'll be very happy to know that logging file systems really do help us. How many of those of you who are writing file systems for on-disk structured file systems are planning on supporting logging in your file systems? 3, 4. Okay. Might suggest that you look at doing some of this. It's really not that bad, and Tom Miller, the guy who did the cache manager, designed a lot of this along with Gary Kimura, our file system supervisor. You should talk to those guys about how you might integrate some of that in your file systems so that users really do see NT as a robust system. NTFS supports Unicode file names on the disk. That is to say, we don't convert from, at the Windows NT level, everything is Unicode. Levels above that, whether it's POSIX or Win32 or OS2, obviously Unicode isn't necessarily the type of naming that we're using. But when you get down to that line that crosses from user mode to kernel mode, at that point everything's Unicode. So you're going to be asked to deal in Unicode. This makes it very easy to internationalize things. We don't have to worry about, well, what code page are we in, and which byte of this thing tells me that there's another byte that's part of the same byte that's the character, et cetera, et cetera. Everything is 16-bit characters. And then the NTFS file system also supports long file names and auto-generates 8.3 names. This is particularly helpful in a server environment where you have applications from different clients that don't understand long file names. Now you can, when the DOS client on some workstation somewhere says, well, I'd like to be able to run this application and get to that file that you just created that was called, hi there, this is my trip report of the vacation that I just had in Europe for 2 weeks. I don't know how to do that and can't even see it today. If you were to do a directory of, if you were to look at a directory from DOS that had long file names like that, it just wouldn't get seen at all. So what we've done is we've auto-generated an 8.3 name so that you can give that name to someone and they can use it. NTFS supports security. Robert Rochelle will actually sit down with you and do a hand-walking, here's what you have to do in your file system to do what NTFS does to support security in your file system. And those are made possible through ACLs. NTFS is extensible. You can add enhancements to it without obsoleting existing volumes. That is to say, every time that we come out with a new version of the operating system and we decide we want to upgrade what we're doing inside the file system on the on-disk structure, we will still support all the old stuff. We do have conversion utilities from FAT and HPFS to NTFS, although one of those will be going away in the next release. Take your pick as to which one you think it is. NTFS is the only secure file system in Windows NT today. That is to say, if you would like to run in a government installation and therefore you need C2 certification, then your volumes must all be NTFS. It can't be FAT for obvious reasons. Another component of the Windows NT Executive is inter-process communication. This allows two processes to actually communicate with each other. This is the mechanism that we use between the client application subsystem DLL and the subsystem process itself to pass information back and forth between those two pieces to emulate an operating system interface. There are provisions for a very, very fast LPC, which I'll show you in a minute. For RPC, when RPC can recognize that it's on the client and the server are actually on the same processor, then we actually use LPC to go do this because it's obviously considerably faster than going through some network protocol to get to the other guy if he's already on the same machine. You can do things such as share address space and stuff like that to talk to each other. And the server can impersonate a client's security context. This is really helpful for, let's say that, for example, Win32 actually used a subsystem process to open files. So when you call DOS open rather than calling Windows NT Executive itself, what you would do is you would RPC or LPC over to the subsystem, then subsystem, it goes to open the file, wants to open the file as if it's you, the client. So what it wants to do is impersonate who you are based on this port. It simply says, I want to have the security token of the person on the other end of this port, and now I'm you. Now I do the open, and I either succeed or I fail based on who you were. Okay, so one type of inter-process communication is via this port that I just talked about. Basically what happens is the client application takes and marshals the DLL, marshals all of the arguments that the application has given it inside the DLL, and puts them in a shared memory segment, which is optional. It could just put them in a message and send them to the environment server on the other end, and then the way it does it is it takes those things and takes those arguments and puts them into this LPC port, which causes the guy on the other end who's waiting for a message to show up in that port to wake up and then either take the datum out of the port message itself or out of the shared memory communications region, depending on how you've implemented it. At which point the client application or the client DLL is now in a wait. It's sitting around waiting for the server to get finished and send a reply back. And the server can actually do a callback at this point, which makes things even more complicated, wake up the client DLL and say, okay, well, you gave me all this information, but I also need some more information. Give me this stuff as well. Okay, so you can actually do callbacks this way. This is a pretty quick way of communicating. There is even a faster way, however. In this particular case, what we're going to do is rather than using a message port, if you know that you're always going to take your arguments and put them in some shared memory segment because they won't fit in the message because they're variable length or what have you, then what you can do is you can use what's called an event pair, and you take the client application, calls the client DLL, passes the arguments, we take the arguments, shove them in the shared memory, and then say, I would like to tell the executive, I want to go to sleep, and that guy over there is the guy that I want you to execute next. And based on the scheduling algorithm system we try and make, the guy on the other end, guy who wakes up, he then wakes up, performs the operation, just sets the event, and you're all finished. Okay, process structure. I said before that Windows NT, the executive itself doesn't impose any protocols or any interrelationships on objects. The process structure in our system simply implements a low-level, hi there, this is what process looks like. We provide processes and threads. It's very simple process structure. There is no hierarchy or grouping. There's no interrelationships imposed on any of these things. If a thread creates another thread, it just created another thread. It's up to the operating system emulation subsystem to decide what the interrelationship between those two guys are. And process structure also provides quota and statistics for each one of those. Security is another executive component. There are two pieces of security, as I said before. There's also a security subsystem that sits out in user mode that handles such things as user profiles, who am I, et cetera, et cetera. This component of the operating system is the guy who actually implements all of the policies that we have for what an ACL looks like, what tokens look like, et cetera, et cetera. This is the component of the operating system if you write a secure file system you need to be aware of so that you can call the appropriate APIs to decide whether or not someone has a particular type of access that I was talking about before when I was talking about files. It then also provides provides access and support for file system ACLs. Okay, so what's the kernel? If what we just talked about was the executive, what's the kernel? I showed you in the picture before. See if we have another one of those. Yeah. The kernel is a very, very small piece of the executive. It's a component. You could actually replace this component just like you could any other one. It has a very well-defined formal interface. It is the lowest layer in the Windows NT Executive. It is where almost all of the hardware-specific or processor-specific architecture support is. There are some pieces of that which are in what's called the HAL, which is the hardware abstraction layer, which the kernel actually uses along with other components of the system to perform some of the functions. But things like how we get the system booted and initializing a processor and stuff like that is all part of the kernel. It provides the lowest level synchronization primitives to the rest of the executive. So if what you'd like to do is acquire a spin lock, it's actually the kernel that's going to go and implement that particular function. This slide right here shows a pretty good view of where the kernel resides in all this. As you can see, it is the part that talks to the platform interface. And platform interface in this particular case you can think of as the privileged architecture of a particular processor. So you'll note that there are pieces of the kernel that talk directly to that, and there are pieces that talk through the hardware abstraction layer that then talk to the platform interface. You can see that device drivers talk to both pieces as well. There are also pieces of the device driver which talk to the platform interface via the kernel. That's kind of hard to draw that interrelationship. Excuse me. Okay, so the kernel, the kernel component of the system is a very small, well-contained body of code. What are some of the things that it does? Well, it provides scheduling. It provides the support for scheduling and context switching. Scheduling in our system, there are 32 different levels of software priority for processes and threads. Half of those are normal, and the other half are real-time. Normal processes can get such things as scheduling boosts, which are things that you're going to need to worry about when you go to complete an I/O operation for a client. You need to be aware of what kinds of boosts do I need to give the person who's waiting on this I/O operation to complete. That will affect the kind of response that users see when they're using the system in terms of I/O. Context switching simply means that we're going to the kernel is a component that supports context switching between different threads within the system. It provides MP synchronization. I said before that if you were going to go acquire a spin lock, the kernel is the place that you go to do that. There are very well-defined interfaces for how you go get access to a spin lock. There are very well-defined rules about what you can do with that spin lock, what you're allowed to do while you're holding that spin lock. There are guidelines for how long you should hold that spin lock, et cetera, et cetera. We'll be talking about all of those things in the next couple of days. The kernel is also the component of the system that performs exception and interrupt handling. I'm going to define what we refer to as an exception as being an exception is how should I define exception? Exception is a fault or an abort that occurs as a direct response to the execution of an instruction. For example, an exception might be a divide by zero exception or fault, i.e., you were executing along a stream of instructions and you executed an instruction that caused the system to fault, i.e., you did a divide where the divisor was zero. Another example of an exception would be a page fault. You executed an instruction which touched a page that did not reside in memory, or not in your virtual address space anyway. In those particular cases, what we have to do is we're going to go fix those things up in the case of a page fault, or we're going to reflect that back to the user application. But the main thing to remember is it's a direct result of an instruction that you executed. An interrupt, on the other hand, is an event that occurs as the result of something external to the stream of execution that you're currently executing. That doesn't define it very well, does it? That is to say, it's not an event that occurs as a direct result of an instruction. It's something that occurs outside of the stream of execution. For example, a device interrupt, an NMI interrupt, et cetera, et cetera. Some of those things, well, that's okay. We'll continue. The architecture for the kernel also provides low-level hardware functions. And as you can see, it's approximately 60K of code. The kernel is partially pageable. That is to say that we can page out pieces of the kernel. We can page out pieces of the executive. It's not preemptible. That is, once you get into the kernel and you have acquired the appropriate locks, you can now not be preempted. Okay, that's a very important concept. You can, however, be interrupted. So while the kernel is executing along, you cannot get back into the kernel on the same processor as a result of a user mode call or a kernel mode call. However, you can service device interrupts. The kernel supports abstractions in the form of either a dispatcher object or a control object. A dispatcher object is something that you can wait on. A control object is something that you use to control what's going on in the system. It also provides generic wait operations that have timeouts, and you can wait on these dispatcher objects. And it provides the express client-server wait operations. The event pair that I showed you before for synchronization is how we do that. Dispatcher objects that we provide in the system allow you to control what's going on in the system in terms of who's executing and synchronization. These things have signaled states. That is, you set an object to a signaled state or you set it to the not signaled state. When something's in the signaled state, then waits are satisfied. When something is not in the signaled state, that is, it's in the not signaled state, then a wait is not satisfied. Examples of dispatch objects are threads. A thread is the basic schedulable entity inside the system. As I said before, the kernel is the guy who supports who executes when, et cetera, et cetera. It also supports mutual exclusion. These are locks that allow only one thread to execute. Events, of which we have a couple of different kinds. There are notification events, and there are auto-clearing events or synchronization events. A notification event is the type of event that when you set it to the not signaled state, everyone that was waiting for that event is set to the ready state. In the case of an auto-clearing event or a synchronization event, one and only one of the threads that were waiting on that particular event gets woken up, set to the ready state, and the event is automatically cleared. Hence the term auto-clearing event. Semaphores are normal counting semaphores. You can have binary semaphores or counts. We support timers, absolute and delta timers, and then the event pairs that I showed you before in the LPC part. The control objects that the kernel provides are not waitable. That is, they do not have a signaled or a not signaled state. The first type of object that we support in the kernel is called an APC, an asynchronous procedure call. And the second one is called a deferred procedure call, a DPC. These two things are sort of similar, but there's a very important distinction that if you don't remember anything else about these, remember this one thing. An APC, an asynchronous procedure call, is directed at a particular thread. When I'm in the I/O system and you've told me that you'd like to complete an I/O operation, in order to complete that I/O operation, I have to take the results, the state that you gave me at the end of that operation. I have to somehow set that in the variable that the thread said that it wanted to have set when the I/O was completed. In order to do that, I have to get into the context of that particular thread to set that state. I do that with what's called an APC, an asynchronous procedure call. I tell the kernel, I would like to execute the following piece of code in the context of that particular thread. Okay? At some later point, when that thread executes, the kernel will take that thread and execute that particular routine. A DPC, on the other hand, a deferred procedure call, allows you as a file system or device driver writer to say, I'd like to have the following piece of code executed at some later date, but it's not tied to a particular thread. Okay? A good example of this is when a device interrupt occurs. One of the things that we want to do is we want to execute the interrupt service routine for that particular driver as quickly as we possibly can. So we're going to suspend whatever it is that we're doing in the system, and we're going to synchronize the execution of that interrupt service routine with that driver running on all the processors in the system, and then we're going to call it. What we want that interrupt service routine to do is A, stop that device from interrupting, get the minimum amount of state that you need to get, and then post one of these DPCs. Post a deferred procedure call so that we can execute the rest of your handler later at a lower priority and then dismiss that interrupt. Okay? What that allows us to do then is it allows us to handle as many device interrupts as we possibly can so that we don't get data overruns or whatever, and yet still be very responsive to everything that's going on in the system. So when the interrupt occurs and you make your device stop interrupting, you then say, I'd like to continue some more code. I want to execute some more code, but I don't have to execute it in a particular thread's state. Okay? Does that make sense to everyone? Great. Okay. I saw 3 people nod their heads, so I'm going to assume that means yes. Okay. The kernel also supports processes. Now, there's this kind of funny thing going on here where I told you before that the process component of the executive is the component that implements processes. Now what I just told you is the kernel is the component of the executive that implements processes. So what's going on here? What's going on here is the process that the kernel implements is the basic process within the system, and it's the control mechanism around which the executive process structure component uses to implement a process object from the object managed point of view, and those are the user visible processes. Okay? So there's 2 different kinds of processes. This one is a subset of the other. Okay? So when the process structure component wants to create a process, it simply calls the kernel and gets back a process. That is a part of a full process that users see. Another control object that the kernel implements is the interrupt object. This is the object that allows a device driver to synchronize its execution of functions inside the device driver with interrupts. For example, if a user, a processor 0, comes into a device driver and says, "Hi there, I'd like to start the following operation on on your device," while the device driver is programming the device to perform that operation, you don't want the device to interrupt that device driver on another processor. Otherwise, everything gets very, very confusing. So what you want to be able to do is you want to be able to synchronize the execution of the control of that function with interrupts coming in on other processors. This is what allows you to do that. And we'll talk more about interrupt objects in a little while. Another one is a device queue. A device queue is used for a device driver to allow one and only one operation to be performed individually on a device. And we allow you to insert them we allow you to insert IO requests in a device queue, either in the order in which they came in, FIFO, or in some priority order based on let's say, the address on the disk that we're going to go to, so that we can optimize seek head movement. And then finally, profiles, which is the other object. And what this allows you to do is allows you to figure out where a person has been executing. Okay, so in summary, Windows NT is a contemporary operating system design. I'm sure that all of you would agree that it's certainly more contemporary than DOS and Unix and et cetera, et cetera. We do provide compatibility with operating systems in the past. We provide portability. We've proven that in the ability to run on multiple platforms, and there are other platforms coming down the road that we will support, some of which you may have heard about in the press, but we're not going to talk about. It is secure, and you need to worry about security. I would strongly urge you, if you're working on a file system or a network system, to put security in your file system if it already doesn't have it, and we can help you do that. It's extensible, and the other thing is it's scalable. As you add more processors to the system, we scale. Okay, let's take 5 minutes or however many minutes for questions. I'd like you to, if you can, only ask questions about this particular presentation. If you ask questions about presentations that are coming up in the future, then I'll simply say, we'll cover that later. If you have questions about anything that I just covered, I'll take those now. Yes?
Talk about the control objects and the interrupt and what to execute as quick as possible. I've never seen any documentation, any standards. How do you make a decision whether you need to create a DPC or you can actually fulfill all your needs in the interrupt?
If the only thing that, okay, sorry. His question basically was, when we were talking about interrupts, we were talking about getting into and out of the interrupt service routine as quickly as possible, and then we were also talking about using DPCs to offload some of the processing. He's never seen written down any guidelines for what you should actually do in your interrupt service routine and what you should actually put off to a DPC. My answer to that question would be you should do as little processing in your DPC routine as possible to make the device stop interrupting. Or make the interrupt, sorry? Oh, did I say in the DPC routine? Sorry. In your interrupt routine, you should do as little processing as you possibly can. Make the device stop interrupting. If you're an RS-232 port, and what that means is you have to go read the character out of the device register, and that's going to make it stop interrupting, and that's the only thing you needed to do anyway, then there's not much point in having a DPC. Right? If, however, this is an AT disk controller, and the interrupt says that there's now an entire, sector of data sitting in a buffer on the device, that's something you'd want to go do in your PC routine. In other words, what you want to do is you want to make the thing stop interrupting as quickly as possible and do everything else in your GPU routine.
Let me give you an example. I can stop it and it gets a half full. I can stop it by putting a byte out there. The half full lag goes away.
Right.
But I really want to fill things up, but it's going to take more time. Would I put a byte out there and stop it interrupting, and then delay the rest of filling the same byte code in GPC, or would I try to do it all in the interrupt?
Okay, so the question is, he furthered the question by giving me an example of, let's say that we have a FIFO, and the thing's going to interrupt me when it's half full. I can make it stop interrupting by putting in a single byte, or I can continue to put more bytes in. Those things are judgment decisions. I mean, how long does it take to write to the FIFO? If this, and I'll cover some ways of doing this in future talks. But if I can write one byte in, 10 nanoseconds, and I can write 10 of them in 10 nanoseconds. 10 nanoseconds isn't very long, right? Go ahead and write the stupid things. If, on the other hand, I'm going to write one byte into the FIFO and I'm going to wait for 10 milliseconds before I'm allowed to write the second byte, get the heck out of there, right? So it's a judgment call. And you'll be able to do testing to determine which is the right thing. In some cases, in our network and disk drivers, for example, one of the things that we were finding was we got into the interrupt service routine, made the thing stop interrupting, and then before we were finished with our DPC, we got another one. Well, it turns out there's a mode that you can put the device in that says, if I'm going to get another interrupt now, don't interrupt me, right? Just set the flag that says you got more data for me. And then in your DPC routine, you can look to see whether or not you got more data since the last interrupt, right? And you want to handle as much of that as you possibly can. Yes?
You said that there are well-defined interfaces for each of the subsystems, like the kernel and so on and so forth. Where can we get documentation?
Okay. The question was, I said during my presentation that there are well-defined formal interfaces for each component in the system. Where are those things documented? They're documented in an internal document inside of Microsoft. No, seriously. The interfaces that you will need to use will be in the file system device driver writer guide. Okay, and there's a person who's been working on that for quite some time. We aren't publishing yet all of the interfaces. I'm only interested at this point in publishing the interfaces that you need to use. For the ones that device drivers need to use, they're in the DDK documentation. For the ones that file system drivers need to use the DDK documentation and supplement that with the file system driver documentation, and that will give you a lot of them. I don't want people to use interfaces, even though they're well defined internally, that we haven't exported in our header files explicitly, because we haven't done that. We know that no one can be using them, therefore we can change them.
Right. You talked about like a university or something.
That's right.
Can we get that documentation?
Right. Universities will, in the future, when we have time to document this stuff, when we have some people working on this stuff, right? Documenting all this stuff, I'd say that's quite a ways out, because the person who's doing that is currently working on the file system stuff as quickly as she possibly can. At some point, she's going to get finished with that. It isn't going to be today. The stuff that you're going to get in this thing, the documentation that you're going to get at the end of this thing, or I don't even know if you've already got it. Great. You've already got it. Is very preliminary. Okay. This stuff takes time. It's going to take you time. It took us a long time to put the DDK together. It's going to take us even longer to put a real file system file system developers kit together. This stuff's really complicated. It's really hard to get right, and there's a lot of it. Okay.
Thank you.
You're welcome. Way in the back.
The guy in the doorway.
Guy in the doorway. No questions. Okay, right here.
Yeah, there are, however, some of those kernel APIs that are important for example, for such things as performance monitoring and query process and that kind of stuff that, would be very useful. And could we get at least some of those?
Okay, so the question is, or the suggestion is that there are other APIs which we're not documenting today that people can use, such as NC Query Performance Counter. why can't we go ahead and get those? We will certainly be adding as many APIs as we can add as we go along. Okay, so for performance monitoring, those kinds of things are important, and we should add. And we'd certainly like to see a list of the things that you think that we should do. Yes.
Yes. You mentioned earlier talking about guard pages. Are guard pages used just for user mode stacks? Are they used also for the kernel stack? And what are the limitations on the kernel stack?
Okay, so the question is, we talked about guard pages before being used for user mode stacks. Is that the only thing they're used for, or are they also used for kernel stacks, and what's the limitation of a kernel stack? They are, I'm not sure what they're used for besides user mode. They're not used for kernel mode. Kernel mode stacks are fixed at 2 or 4 pages, something like that. That is the limitation. There are no more pages in the kernel stack. Okay, so when we start talking about layering of device drivers and stuff like that, you need to be aware that we don't automatically expand kernel stacks, and that's really important. The reason that kernel stacks are as small as we can possibly make them and still get away with it, and we have lots of drivers that use lots of stack, and we've got 5 and 6 layers deep, and it works today. There are techniques for making sure that that works. The reason we don't do that is because kernel mode stacks, once they're there, can't go away, and we only have a fixed number of pages because those things must exist for every thread in the system always, unless the thread is performing a wait operation on behalf of a user and you can't possibly get into kernel mode, then we can page those things out. But the rest of the time, for every single thread, you have a fixed number of pages locked down inside the executive while that thing's running that we can't do anything else with, so it's really expensive. Yes?
Well, since you've heard of interrupts for so long, I have a rather long list of questions. I wonder whether you can
Can you speak up? I can't hear you.
I said I have a rather long list of questions, and I'm wondering if...
Okay, how about if I take long lists of questions offline?
Okay. All right.
Okay, let's
During the break?
excuse me? Yeah, I'll see you during the break. One more.
What's the relative cost of a spin lock versus a mutex?
What's the relative cost of a spin lock versus a mutex?
I'm looking for a guideline for choosing one or the other synchronized threads in a file system. So I'm not worried about synchronizing with interrupts.
Okay, so the question is, what's the relative expense of a spin lock versus a mutex? And he's using these two locking mechanisms within a file system, so he doesn't care about synchronization with interrupts. The answer to that question is the guideline that I like to use is that if you're going to hold a spin lock, you should never, first of all, getting a spin lock is a very cheap operation. Getting a mutex is a more expensive operation, or it can be. However, if you're going to get a spin lock, first of all, you shouldn't hold a spin lock for more than about 25 microseconds. Second of all, if you own a spin lock, anybody else on any processor trying to get that cannot do anything else except for spin on that lock. On the other hand, if you get a mutex and someone goes to get, if someone wants to acquire that mutex on another processor, then if you own it, they get to go into a wait state. Okay? Now we can do something else with that processor. We're not going to sit there and spin at a raised IRQL, a raised interrupt request level, waiting for you to get done with that thing. So in essence, they should be very short-term operations. And, okay, so that's, yeah. Okay, so let's take a, there are lots of more questions. We'll take them, I'll take more during break, or you can ask them after the I.O. presentation. Will we have a 15-minute break? Yeah. Okay, let's take 15 minutes. Thank you.